Back recording. It's a Sunday morning, and I'm doing a little. Right. Back. Okay, audio is good. It is Sunday morning, and I'm doing some more work. I'm gonna go on a run later, but it's a little chilly out for that right now. It's gonna warm up quite a bit. It's at 58, so it's not too bad, but I actually enjoy running when it is really hot out. Mid 70s is my favorite temperature to run. So if you're just joining us, this is me making a course live. You're watching me make a course from scratch. And it will be on building a layer 2 leaf spine fabric with Arista EOS. It's not affiliated with Arista at all. I'm just doing this on my own. I used to be a Arista instructor. I didn't work for Arista, but I contracted with them. But I no longer do that. So this will be so I'm going to put this course out for free. Layer 2 leaf spine is, you probably have heard it as a collapsed core. It looks, we have the traditional core aggregation access layer. We've been building this type of network for like 20 years now. Although mostly in the past couple years, the core and aggregation layer have collapsed into a single layer because of the way hardware goes. So this is what it looks like. I guess we'll call this core 1 and core 2. All right, so continuing on, describing link aggregation. I'm doing animations. I like doing animations because I think they're more engaging with the audience versus reading slides. And they're a lot more legible than chicken scratch on a tablet. So not to say that whiteboarding with a tablet's not a good idea. I think it is. I just don't think it's a good idea to do an entire course like that. I have done it like that before, but I think why do it on a whiteboard when you can do an animation for not a lot, you actually save time this way, and it's way more legible. All right, so enter link aggregation, build the interfaces. We do a flood and learn. And yeah, okay, so looks good. Now we need to talk about LECP. I have a, what I am proud to say is probably the definitive guide on link aggregation and LECP. It's on YouTube. And it talks about the differences between them. They're often conflated with each other, often confused with each other. So what does LECP do? I'll build a slide. What does LECP do? The only thing LECP does is determine which links in a configured lag, which Arista calls a port channel, will forward. LECP does not choose. LECP is not the mechanism that divides traffic amongst links. This is one of the most common things that I see in networking. Even higher level network people make this mistake. When I started teaching for Arista, I took a look at their LECP deck, and it was wrong. They, like, the guy who wrote it was flat out wrong about LECP, because he was talking about he wrote it as if LECP was the same as link aggregation. LECP is part of link aggregation, but it's not link aggregation. When a lot of people say LECP, they really mean link aggregation, because you don't need LECP to do link aggregation. It's a good idea. I always use it, but LECP does not divide traffic across links. The only thing it does is determine which links in a configured lag will forward traffic. LACP is a good idea to turn on with every lag port channel. I'm trying to think if there's any situations where it's not a good idea to turn on LACP. I think probably, I can't think of any. Not to say that there aren't, but I've never run into one. The only time that I didn't configure lag is that Cisco years ago had a load balancer called the ACE. And it was a piece of garbage. It was a load balancers in Cisco have not gotten along. They had the local director in the 90s. It was part of like I think it was an offshoot of the PIX firewall. This is the same hardware. And then they bought a company called AeroPoint, and that became the CSS, the Content Service Switch. I think that's what it was. And they let that just kind of, you know, they bought the company for like $6.7 billion for a load balancer. But that was one of the hottest technologies back in the late 90s, early 2000s. And load balancers actually killed Linux, or not Linux. Load balancers killed Unix because load balancers made it easy to scale out instead of scale up. So rather than buying more and more expensive, more cores on a Unix server, which were tens of thousands, hundreds of thousands of dollars, you can just buy a bunch of Dell pizza boxes, put a load balancer in front of it, and then scale out. Which seems obvious today, but that was new back in the 90s. Anyway, so they had a load balancer, the CSS, and that kind of atrophied. They didn't really do anything with it. And then they created their own, I think this was homegrown, called the ACE load balancer. They had a line card for the 6500, and then they had an appliance called the ACE 4710. And it wasn't very good. It didn't do a lot of things that other load balancers did. But one of the things that the appliance did not do is it did not do LACP. You could configure link aggregation, but there was no LACP and no PAGP either. So that was the only device I've ever configured that I didn't do LACP on. So so there might be reasons not to do it, but I can't think of any. LACP is a good idea. LACP can be used for switch to switch links as well as host to switch links. So I turn it on anytime any port channel should have LACP if possible. Yeah, every now and then there's devices that don't support LACP, but I haven't run into any since the ACE load balancer, and that got discontinued in like 2013. So it's been like 15 years, or close to 15 years since that thing was around. Yeah, it wasn't very good. Just get an F5. And how does it work? So here, we don't need forwarding tables for this, because it doesn't really do anything with forwarding tables. We don't need the hosts for this. I'll move this down. I'm also going to make this a group, so I can make it a little bit bigger. Then you hold down the shift to keep the proportions, and then I'll increase the font just to make sure everything's visible. I don't think I need these either. Okay. And then I'm going to do a configuration dialog. So do that in text. Fill it. Yeah. And then this will be GitLab mono. Shrink it down to 12. And make it white. I forget, does it capitalize? So this is why it's good to have. Oh, did I turn that one off? I got to turn on my VM. My hypervisor's off. I'll be right back. My hypervisor's off. All right, let's see what's going on there. When it boots up. All right, so we'll do this. Copy and paste. Four and 5. Move this up. I think I will actually put these back. So we get the config, and then we want to send some LACP PDUs. And my hypervisor's back. I don't know why it had shut down. Start up my VM. So this VM is running Debian 13. It's real fast to boot. So I started it like 10 seconds ago. Let's see how long it takes for this to come up. Yep, and it's already up. which is pretty phenomenal. So it always helps when I'm doing commands to make sure that the commands look right by having a system I can test the commands on. Also, I need some images of what the LACP show commands look like. Because if you're going to build a layer 3 leaf spine or layer 2 leaf spine topology, if you're building a layer 3 leaf spine topology as well, you need to know how LACP works. It's one of the most misunderstood protocols in terms of what it does and what it tells you. And just spending a little bit of time learning it. It's not complicated. It's actually very, very simple. But once you learn what it does, a lot of troubleshooting becomes a lot easier. So, and an example here. Actually, I should probably just do these. No, I do not want to do that. So the example I always use is a coffee maker. LACP can help. It's like a miscabling protocol. It can help you in case you accidentally plug the wrong thing into the wrong thing. Make a icon for a coffee maker connected to Ethernet. Make it a completely transparent background with a pastel color scheme in a simple minimalist style. And it's going to take like 12 minutes to do this. All right, are we done here? Yep, we are. I think it reconfigured everything. So like leaf one. Yep. So I have a playbook here. Oh yeah, I've got to there we go. I had to activate my Python environment. So it's just a quick playbook that'll go in and yep, there we go. Do a quick config. E1 interface E1 and 2. Let's go to spine 1. And then I'll go to spine 2. So the link is up. So this is the output I want to see, because this will be important. I'm going to paste this output into that window. Need to come up with a color scheme so that is obvious what we did. So the way that LACP works is it sends LACP PDUs across every link. So do a call out. Background. Let's see what it's going to come up with. So an LACP PDU contains the system ID, system priority, hopper key, which is a port ID, and port priority. I think that's it. Yeah, that works. So what do all these things do? You can look it up in the see what it's got an AI mode. Transmitting the frame. Okay, that's what I was confused about. I didn't know if the port ID... Man, this thing is taking forever. It's freaking... Oh yeah, because I made a new slide. Okay, system ID, system priority. It should also be talked about what LACP did, but doesn't really do anymore. Link aggregation used to be limited to 8 interfaces in a lag. This was a because of a 3-bit hash. Only 8 buckets for dividing up traffic. I'm noticing a layout mismatch. And this thing is like taking forever. There we go. Not exactly happy with the outcome because you get that weird thing in the middle there. So I'm just gonna crop it. If you had a lag with 10 links, there needed to be a way to determine which of the 10, which 8 of the 10 would be active. System priority would determine which side chose the active links. Port priority would determine which interfaces would be active. Most lag implementations, including Arista, support way more than, well, more. Way more sounds a little too formal. Well more than 8 links in a lag. So can I make this a slide? Probably. Make this a picture rather. Probably. So I'm going to ungroup these. And then I will take this picture and I will double it up. So I have 10 links. I don't need those. Oops. I'm going to run the arrange, and I will distribute that way. And I'll do the same thing over here. Okay. I'll also make this text a little smaller because I'm going to double digit them. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it used to be that there was a limit on 8 links, a limit to 8 links. But now we've got 10. We put them in a port channel. Only 8 of them can be active. How do we determine? So we have a system priority. Right. And I believe it's the highest. This is one of those things where, like, I don't remember if it's the highest or lowest. Typically with layer 2, it's the lowest, but I think with LACP, it's the highest. Which wins in system priority? The lowest priority wins. Okay. Yeah, generally the rule of thumb is that for layer 2, it's the lowest value that wins the election, and in layer 3, it's the highest value. Like think about VRP priority or different priorities. Usually, the higher value wins in layer 2, like the lowest bridge ID or the lowest the lowest LAC or spanning tree priority. That's usually what wins. There are some exceptions, I think, although I can't think of any right now. Yeah, lowest MAC address wins. But this is not something that's really important to remember because we don't really use LACP as a selection criteria. I think it is, if I remember right, I think it's hex. So we do port channel 10, LACP, system ID. How do we configure LACP system priority? I've never had to configure that in Arista or anywhere, actually. This may be going too far down a rabbit hole. It may not be worth doing all this work, but I'm curious. Configure system ID priority. Arista EOS. LACP. It's a global config. Makes sense. Let's do 2. Show LACP here, all out ports. See what the other side says. Show LACP. Here, all ports. 2. Okay, it is. No, it would be hex. So I think it's hex. So let's do. We'll do 12. Sometimes it's hard to tell if a value is hex or not. It said 8,000, and that kind of. So it looks like it's decimal, but I think it's hex. Yeah, it's hex. What is 8,000 in hex? convert 8,000 hex to decimal. 32,768. Interesting. I guess that makes sense. Make this smaller. $16. Might need to do, yeah, let's do this. I'll do a separate text box for it. So system ID. So I will do an animation where we do the system priority of 1, and then it would become the decider. Yeah, so let's talk about the information that it gives you. System ID, system priority. Port ID. Oper key. Lag ID. So the oper key is the lag ID. And then port priority. Yeah, system ID, port priority. A lot of work for a simple concept, but that's the way it works. And then we'll do a LCP PDU. So the opera key would be 0A, which is 10. Because it's the port channel ID is 10. Port 1. State. What does the state mean? Oh, yeah, I think it's in there. Yeah, state. ALG is so active, long timeout, aggregable, plus collecting and distributing. I don't know what those mean. Let's look them up. Yeah, one of the things about teaching, whenever you're teaching something, you learn a subject more, you learn a subject better when you're teaching it, because then you're like, someone gives you a question or you like find something and you're like, oh, I need to know more about this. Arista EOS, LECP. Because I'm going to come back and we're going to do fallback mode when we talk about connecting hosts. Because some hosts, you want to do LECP, but there's a period of time when it boots up. Maybe it's like doing a network boot, where it doesn't, like the network boot software doesn't support link aggregation. So you want it, if you don't detect at a PDU, maybe you put it back, you put it into normal switch or normal interface mode, non-lag. So you can get this thing started, and then when you see an LEC PDU, then you combine it into a lag. Let's see if it shows us. Why is all this like highlighted? It's highlighted everywhere? Kind of obnoxious. Yeah. What is EOS? Product documentation. What was that? Yeah, I don't know why that's really obnoxious. Okay. Aggregable. All right, I'm just going to skip this part. All right, so port opera key. So what does a PDU look like? Format, shape, text options. Top. We'll do left to right. Do this, and we'll do white. So system. Show it in hex. That's 10 in hex. Yeah. And then port priority. What's the default port priority? 32768. So I'll shrink that down. We'll make the text bigger. There we go. All right, I'll be right back. Hit the restroom, get some more coffee. So we'll compare the LACP PDUs for two different, because we don't want to do all 10, because that would be excessive. So we'll do it for like Ethernet 1 and Ethernet 5, just to give an idea of what we're talking about. So system priority wouldn't change, the opera key wouldn't change, the port port ID. One. Port ID here would be 5. So I like to sometimes highlight certain things. So we'll do a shape fill of no fill at outline of red, and then a weight of 3. So we can call things out. Okay, so what I'll do is I'll do some animations. Get rid of these. I can get rid of that too. Yeah, so what I should do is make them all have LECP PDUs. It's a fairly simple explanation, and I think a lot of people generally don't realize. People don't even realize. You don't even realize. Sounds like the blogging or the podcast manosphere. People don't even realize. But no, people don't usually generally know what's going on with LECP, what it does and what it doesn't do. Like I said, it has nothing to do with how traffic is divided. It can't even influence well, it kind of can technically, but it doesn't influence the hashing algorithm used. That's configured separately. There was a field added that can communicate what the one side is using, theoretically, so the other side could figure out how to match it if they wanted to match them. But as far as I know, no vendor implements it. I emailed once one of the creators of the standard, and he was amazed that I yeah, he responded back in 2019. You can communicate the algorithm that you're using for load balancing, which would be useful if the other side were to want to match. But it was released in 2014. But as far as I know, no vendor actually implements it. I don't think Arista does. I don't think anyone else does either. Yeah, there's no setting for it. I don't think it's in. I'm not gonna. I could look at the PDUs and see if it's in there, but I don't think it is. Partner churn. Oh, there's interesting. Port priority, partner churn, collector max delay. Is it even in here? Yeah, it's not even. Yeah. So something I've noticed in Arista documentation, there's some stuff missing. So when people say Arista documentation is not complete, this is what I mean. Like, so there's a field, collector max delay, and it's not in the documentation. So it usually gets the basics right, but like sometimes you just don't know. So I've run into this a couple of times. Yeah, so their documentation is not always complete, which is a bit frustrating. Whereas someone like Cisco has like everything detailed down to the last bit. All right, so here's the presentation. All right, we'll go to the animations. So, oh yeah, I probably want to call out the system ID. And the system priority. And just talk about what they do. So I've got two switches. They both have a system ID, which is the same system ID, which is also the bridge ID used in spanning tree. Appear, disappear. They both have a system priority. By default, it's 32.768. Appear and disappear. Now they both send. Both sides are sending these LACP PDUs, which contain appear. And then this will disappear, this will disappear, this will disappear, this, and this will disappear. So we're just going to look at these two. And then we'll make these appear. And then we'll go through them one by one. So we'll appear here and disappear. And then appear here and disappear, and then appear here, and then disappear, appear here, and then disappear. I feel like I'm pronouncing things weird, like the club. Going to the club, no, I'm going to the club. All right, so we have two switches. Each switch is going to have a system ID. That's the same thing as the bridge ID in spanning tree. You can see that by doing a show system. They also have a system priority. The default is 32.768. And that's to determine if we're trying to determine which links are active, one side gets to pick. And this is how we determine which side gets to pick. It will be the one with the lowest system priority. If they match, then it's the lowest system ID. So in this case, switch 1 would decide among these 10 links which ones would be active. All the switch 1, they're both sending LEC PDUs. So switch 1 is sending them, switch 1 is sending them to switch 2, switch 2 is sending them to switch 1. Let's take a look at two of them. So coming one from Ethernet 1, coming to Ethernet from Ethernet 5. So let's look at the information in them. So we have the system ID. So that's got to match. For this lag to come up, the system ID on all the links in a given port channel, all the links in a given lag their system ID must match. So this will ensure that we're plugged into the right device. There's a system priority. We don't really use it because all of our links are always going to be active. because we can do more than 8 links, so that's not really a reason. We're just not going to use system priority, so we can ignore it. It also tells us what port ID it's coming from. And then an oper key, usually given in a hex, but that's going to be the port channel ID. That also has to match. So both the system ID and the oper key have to match. And then we have a port priority, which is used to determine which of the links, the ones with the lower priority, will be active. And if that doesn't work, it's the lowest port ID. But again, the priorities you can pretty much ignore these days in modern times, because we don't. Okay, so that I think it's sufficient to describe the LACP PDUs. And if you have a question about LACP PDUs, you can put it in the chat, and I will talk about it. So I'm starting to build up some nice slides here. These are all custom made. You've watched each one of these slides be created. And you can watch how I make the slides. Okay, so let's do without LACP, and we'll do with LACP. I did something similar to this in my in the video I did. Oh, this should be without LACP. Oh, with and without. Out LACP. I need a checkmark emoji. So copy it. Put it in here. There we go. And then I'll do the config. Okay, so so we show the config here. Maybe I'll make this a little bit bigger. And I'll do a call out for the language, or for the part. So the mode on part means that we're not doing LACP. So it's link aggregation without LACP. So the links forward so let's do the animations. Oh yeah, I want to do one more thing. I'll do make this traffic. Need a good color. Need a huge weight. Yeah, okay, I like that. So we'll do animations now. So when we configure a link, this is the same config on both sides. When we do mode on, oh, I did not do that right. Animation pane. Let's get rid of that. Okay. So that comes in, stays. That comes in. Let's go ahead and get rid of it. So we'll disappear. Actually, no, let's do this. And that'll configure the port channel here. And if we do the same config on the other side, it'll do the port channel here. Okay, so and now we have a port channel. Do I want to show this? Yeah, I don't want to show this. Okay, so move this over here. Yeah. Okay. And then I'll show this mode on. So if we do that and the link lights are up, then we're going to send traffic on this side and on this side. And I need the red X emoji. $32. These are $40. There we go. But this one is off. Because the link lights are up, some traffic will get hashed out to the coffee maker. All right, let's say I make a misconfiguration and I plug it into the coffee maker. So I'll move this all the way up. All right, so I've got two switches, switch 1 and switch 2, and I connect them. But in the process of connecting them, I miscable Ethernet 5 on switch 1 over to a coffee maker. Let's pretend a coffee maker has a 100 gig interface. It's a really big coffee maker. So when we configure the port channels, we're going to use mode on. And what that's going to do is we'll configure the port channels on both sides. Mode on means that we're not going to use LACP. So I think this should be 5 should be in front of them. So when we do mode on, it means that the links are going to be without LACP. They're just going to be a static lag, static port channel. Static means they're not using LACP. Now, the thing is, without LACP, the traffic gets divided the exact same mechanism. So LACP or no LACP, there's no difference in how the traffic gets divided. But without LACP, the only thing that link aggregation checks to see if we're going to send traffic down a link is, do we have a link light? And on the switch 1 side, we have link lights for all 4. On switch 2, we don't have a link light for Ethernet 5, so it won't send traffic. But switch 1, since it sees a link light on all 4 sides, switch 1 has no way to know that it's plugged into the wrong device, and some traffic will get sent, however it hashes out, will get sent to the coffee maker, and that's no bueno. Okay, so that's without a LACP. I like that. We'll go on with that. And then we'll try it with LACP. So that is mode active. Let's see. Okay, so we do active. Now here we've got 2 links, and I actually plug it into the coffee maker again, but I'm using mode active, so that engages LACP, so we're getting LACP PDUs. So I need to add some LACP PDUs. 2, 3, 4. So I'll have them. Two, three, 4. I'll have them appear and then disappear. And then I'll swappy because they're doing both sides. Try this. Do. PDUs. Links are active. But yeah. Okay, that works out well. I like that. Okay, so we've successfully talked about LACP. Now we should do one about how traffic gets divided. Wonder what we could do here. So port channel. Load balance. Yeah, can't change it on this platform. Should add oh yeah. So what I should do is I should add this to here. Because we have the lower priority, we're gonna I'm gonna go get some more coffee. Okay, traffic hashing. Should do a historical one, 3-bit hash. Because we used to be limited by I'll do it this way. We used to be limited to only 8 links in a given lag. And the reason is switches did an 8-bit hash. And it was an XOR. So let's get rid of this. Because we used to have a rule. So old rule. Make lags a power of 2. Make number of links in a lag a power of 2. 2, 4, or 8 links only. And the reason was it was a 3-bit hash. I did a whole bunch of slides on this. Maybe I'll reuse them. Let me see if I can find them in my webinars. That's Dr. Radia Perlman. I've been mispronouncing it for years. I called her Radia Perlman, but it's Radia. Yeah, so I think I've got a better one. this one? Did one for a webinar. Nope. Because there's definitely been some so these are so a lot of these are diagrams I've made for years. I've been drawing them or putting them on PowerPoint, various PowerPoint presentations. But it helps to refine them now that I got better skills. Like this I made a long time ago, and you can tell that my my skills are getting a little bit better here. But I will copy and paste some of these. So I'm not against reusing stuff where it makes sense. So frame, and then we do a process. Looking for the flow chart. It's just a square with no rounded corners. So we need to go into that detail. So the original switches would do an XOR of the addresses. They would, for one thing, they would lop off the high order bits. They would get the last 3 bits, and then they would XOR the source and destinations until they got a 3-bit hash. So basically, we're hashing to 3 bits. And then we would get a 3-bit value. And then 000 would go here. So the outcome would go here. 001. Zero one zero 011. One zero zero 101. And then, oops, 110 and 111. This should be GitLab. And the problem would come is if we did, so I need to make a copy of each of these, or these at least. Make this a group to make it easier. Make this a group to make it easier. 0001, 010, 011, 100. Okay, looks good. So we added this. We used to have this rule. So I'll do the animations. We used to have this rule where you make number of links in a lag a power of 2. So either 2, 4, or 8 links only. That used to be the rule. It's no longer the rule. And the reason why we have that rule is because we used a 3-bit hash. So a frame would come into a lag. We would then run it through a header. We would run the headers through some sort of algorithm, typically some sort of XOR. Very rudimentary. We'd lop off the higher order bits or whatever. Didn't really matter how we did it. But the process would give us a 3-bit value. And then, but a 3-bit value only counts to 8. So make that GitLab. So then we'd have to take those buckets and distribute them across our available links. So for example, this is how we would distribute those links. But what if we didn't have got to ungroup this. But what if we didn't have one of those links? Then our hash wouldn't work, so we'd have to do a different hash. And algorithmically, the first 2 links would get twice as much traffic as the other links. Okay. So used to be switches, this is like more than 20 years ago, switches would have a 3-bit hash. So let's say we had 2 switches here, and the rule would be that we would have to make a lag a power of 2. So either 2, 4, or 8 links. And the reason was, frame comes in, we do some sort of function on the headers, and we would get to a 3-bit number. So it was a 3-bit hash. Now there's different ways to do this. You could do an XOR, you could lop off the higher order bits, do an XOR, you could do some sort of algorithm. But it used to be the output of whatever algorithm it was would give us a 3-bit value. And you can only count to 8 with 3 bits. So it would be divided across 8 buckets. And we'd have to distribute those 8 buckets across however many links we had. So if we had 4 links, we would do 2 buckets per link. So any traffic that hashed out to 000 would go across the first link. Any traffic that hashed out to 111 would go at the last link. It was deterministic because we have to deliver traffic in order. The problem with the 3-bit hash was, let's say we didn't have 3 links, or 4 links rather, we had 3 links. So the hashing, we couldn't distribute them that way. We'd have to distribute them this way. So the first 2 links would get algorithmically 50% more traffic than the 3rd link. So that's why we used to have that rule. These days, we don't have that rule. We have... because most of the algorithms use a much deeper hash bit. So today, how would I do this? Let's say it was an 8-bit hash, 8-bit value. And then we would get... $256 buckets. So the first one, if we had 256, so 64 outcome, 64 of the buckets, 64, 64, 64. We'd get at even distribution. But if we only had 3, it would be what's 256 divided by 3? 85, 85, 86. 86, 85, 85. I'll make this appear. But that is, there we go. But nowadays we have a bigger bit hash. So frame comes in, we run it through an algorithm. So let's say we get to an 8-bit hash, or there's other methods, other ways to do we can do a modulus. But let's say we had 8 bits for a hash. We get an 8-bit value. That's 256 buckets. So if we divide it across 4 links, it comes out even, just like the 3-bit hash. But if we had only 3 links, it would be 86, 85, 85. So much more even distribution than we would if we did it otherwise. So okay, so I'm good with that. Then we'll do one for why we do we hash. Round robin would mean equal distribution across links. So why do we hash? So so round robin would mean equal distribution across links. But we never, in networking, we almost never round robin traffic across links. We need most traffic requires in order delivery. Not all traffic, not all most traffic, especially TCP. Requires in order delivery. There actually is there's a Ultra Ethernet Consortium, and one of the things that they're talking about is doing for certain type of traffic, you could do a cause value or a class of service where it would spray it across multiple links. The idea it would be for AI workloads where the AI applications would handle the reassembly. So it wouldn't matter. So round robin would mean equal distributed across links. But in networking, we almost never use round robin because most traffic, especially TCP-based traffic, but other types of traffic as well, requires in-order delivery. The only way to guarantee in-order delivery is to send all related packets, TCP connection, UDP flow, etc., through the same physical links in a lag or ECMP path. So for layer 2 and layer 3, we still have to hash for either one of them. Should I do a slide that demonstrates why? Yeah, why not? Let's do that. I've never done, I don't think I've ever done a slide this way to indicate this type of hash. So I need two sides. Get rid of this, get rid of this. I need two hosts. I'll be right back. Get some water. There we go. So the problem comes with I need to make this this in the bottom. So every interface has buffers or queues. So we're going to look at this as a problem in one direction. So do a connection here. Make this yellow. Connect these. Connect these. Then you get the circle because it's a lag. Although it's the same problem with LACP. So we send some packets. And we send them in this order. 1, and then we'll make them orange. Because packets are orange. So 1, 2, 3. So we send 3 packets. The problem is that each of these interfaces have buffers and queues. So we're going to look at the queues for 2 different interfaces for this traffic class. And there's already going to be packets in some of them. I'll do a different color. I could do the moving animation, but moving animations in PowerPoint's really obnoxious. So they'll disappear, and then this one will appear here, and then there'll be 2 that appear here. So this one gets in here. And then 2 and 3 are put into this queue. And then so by the time it gets to the host, comes out of order. So it arrives as 2. Need to do a direction flow there. Direction flow there. So say we have a host on the left sending to a host on to the right. So it sends the packets in order of 1, 2, 3. So we'll do animations. First one. First packet comes in. Second packet comes in. Third packet comes in. Now, in the interfaces, the first interface has 2 packets being sent out currently. So the interface is busy. So the first packet will go into the queue. But the second interface is not full. And let's say these 2 packets go in that one. And then as a result, 2 and 3 go ahead. So on the other side, I should do it this way. Two and 3. because the 2 packet went first, and then the 1, and then the 3B, and then the 3 because it was behind the 1. Okay. So this is why we have to send all packets across the same physical links that are related to each other if we want them in order delivery. So for example, we got a device on the left sending a packet to the device on the right. So it sends them in order, 1, 1, 2, and 3. Okay, so that's the order that it enters switch 1. But because we're doing round robin, the first packet goes into the first interface queue, even though there's 2 packets in front of it. The second one goes into the empty queue. I need to make, yeah. One, two, three. The first packet goes into the first interface. However, there are 2 packets in front of it, so it's got to wait. That's what a queue does. It's a place for a packet to wait. There we go. So it's got to wait. The second packet goes to the second interface. There's no wait, so it goes right through. The third one goes after the first packet. So on the other side, by the time we get to the host, we've delivered out of order. So the first packet that the host gets is the second packet that we sent, then the first packet, then the third packet. That is out of order delivery. So to prevent that from happening, so by doing a hash of the headers, we make sure that all related packets go across the same length. Therefore, they go in the same queue. So again, we send some traffic, 1, 2, and 3. I'll just start over. We send some traffic. It's 1, 2, and 3. Now, the first packet gets sent into the first interface, but again, it might be busy, so it's sending some traffic. And then the rest of the packets go into the queue, even though the other one is completely empty. So this means that sometimes we have congested links and non-congested links because of this. But the benefit is that we deliver traffic in order because it comes out as 1, 2, and 3. So traffic comes into the switch. We, in the order of 1, 2, and 3, we get hashed into a queue. And but there's already packets in there, so we've got to wait. And then the 2 and 3 go in behind it because we're sending all related packets to the same link. And then that way, when they come out the other side, it's 1, 2, and 3. So we can run into some problems with this. Uneven distribution. Oh yeah, I need to make this switch 2. Recording uneven. Switch to. I'm gonna need to make these bigger. Get rid of all the animations. Gets too confusing. Oops. Delete, 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 delete. Arrange, align, distribute. Vertically. Align these. I think they're not quite aligned. Okay. Okay, so I need to make a table with the different header values. So header and value. So Mac source, Mac destination, IP source, IP destination, TCP UDP port, source, fixed destination there. So make all this smaller. And then shrink that down. do some callouts. So most devices can look at things like the source and destination MAC address. Source and destination IP address. And then source and destination layer 4 port. And then some can even do things like VLAN ID or put some other values in there. But whatever the headers are, we do a hash and we pick a link. But if we only have one host talking to one host with one connection, it doesn't matter how many links we have active. Any given flow can only use one path. Do a weight of 6 and then do an arrow at the end. So it's good to have a variety of values. Most devices will default to using those 6 header values, and possibly even some additional ones, like I said, VLAN ID. But the more entropy, the more randomness that we have in that, the better the traffic distribution is going to be. But it's never going to be fully even distribution. And we can have a case where if we just have one connection talking to one connection, or one device on one protocol, then it's only going to grow across one link. Some protocols like SMB take this into account and make sure it spreads SMB traffic across multiple port source and destination port IDs. So that because oftentimes it's a host talking to a file server, and that traffic is only going to go over one path unless the protocol is smart enough that it starts dividing the requests and responses across multiple TCP ports. But most protocols aren't that smart. HTTP used to spread its traffic across multiple links, but HTTP2 does not, because it doesn't have to. Because it is multiplexing better. All right, so that's a lot of... This is a good stopping point. We're right at about 2 hours, so I'm going to go ahead and stop this. I might get to it a little bit later, but I'm going to go for a run and then get some laundry going because it's Sunday and it's time to do all those household chores. So thank you for watching, and I'll see you next time.